For each wave vector little k, there are as many eigenenergies n as we have entries in the matrix. We have used 9 reciprocal vectors big K, so there should be 9 eigenvalues. Let's represent the eigenvalues for all the values of k in the first Brillouin zone. To identify some specific isoenergy contours, we'll use a special color map which jumps color schemes at those isoenergy levels. Ready? Whoa, that doesn't look trivial at all. Okay, so let's gather the isoenergy contours for those randomly selected values of E. At E equals 0.2, we can only find wave vectors in the lowest eigenvalue. At E equals 0.3, we have one branch in the lowest eigenvalue and another in an eigenvalue above. We can carry on for the other selected values of E. In crystal physics, the energies are often represented along a specific path of wave vectors, such as this closed path connecting the points labeled gamma, x, k, gamma, for our example of a square lattice. Let's see what our 9 eigenenergies look like along this path. That looks pretty complex again, but hold on. Each branch looks like parabolas. Let's see what the kinetic energy would look like along these paths. Yeah, that seems remarkably similar. What about the higher energy branch? Well, remember, each system is made of wave vectors built from the reciprocal lattice vectors like big K1. Let's look at the kinetic energy for these waves. Fantastic! Let's look at big K2. This time, it seems that it passed through portions of bands of different colors. Let's look at the other ones. We've coupled all the branches, but the colors seem to indicate that there isn't a one-to-one correspondence between a band index and a reciprocal vector big K. Okay, let's go back to our selected isoenergy contours. And let's focus for now on the second one, which only involves, as seen before, the first and the second energy bands. We can now readily identify the points where the isoenergy intersects with the parabolas. The first band corresponds to the top isoenergy branch in the asymmetric cell, while the second band seems to correspond to the lower branch. We saw earlier that the second band corresponded to kinetic energies using big K1, so the corresponding isoenergy branch should actually correspond to this translated set of wave vectors. Let's now use the symmetries mentioned previously to position the remaining branches. Well, this looks somehow similar to a circle. Well, this is not surprising, since a plane wave Q with only kinetic energies, Q squared, would have circles of radius Q for isoenergy contour. This isoenergy contour representation is known as the extended zone, representation, as opposed to the reduced zone representation, which is the natural output of diagonalizing the Hamiltonian. So, how do the other isoenergy contours look like? Well, by systematically finding the reciprocal vector to which each branch must be translated into full reciprocal space, we can similarly get the extended zone isoenergy contours for the other ones. They certainly look like circles too. Except along some lines apparently, where they seem to depart from the free electron circles. Okay, so now let's map the colors we have for each energy bond to its location in the extended zone representation. They are precisely delimited by those particular lines. There is no doubt those lines must be quite meaningful. Okay, so it looks like, focusing on eigenvalues, we have forgotten about the other important quantity, the eigenvectors C of k. Let's look at the wave function psi in real space that we can reconstruct from the coefficients. Since it is a complex valued function, we may display its real part, its imaginary part, modulus, or more meaningful, squared modulus. Let's look at the first two bonds again and choose one point randomly in the first bond to display its real part. The solution is unsurprisingly close to a sine wave varying along the x-axis. As anticipated, psi does not have the periodicity of the crystal. Now, let's look at what happens along one of those mysterious lines, such as the xk line. Along these lines, two waves with identical wavelength and opposite directions along kx are interfering with one another, forming a standing wave pattern. Let's look at the electron density probability psi squared. For the lowest energy bond, the state is mainly localized around the nuclei, so most often it is attracted by them, hence an energy smaller than the corresponding free electron kinetic energy. For the highest energy state, it is mainly localized away from the nuclei, and comparatively it is more free, hence a higher energy than the corresponding free electron kinetic energy. Note that the real part of the first bond and the imaginary part of the second bond are identically zero, meaning that these two standing waves are oscillating in antiphase with one another. So that's it. The special lines are lines along which waves are somewhat resonating with the periodic electrostatic potential, which explains why the effect of the potential is the strongest around those lines. These lines are known as Bragg planes in 3D, as he was the first to establish their importance in the context of X-ray diffractions. There is one last bit to address. Let's look at the periodicity of the electron density probability for a range of values of k. It seems to follow the periodicity of the crystal. Perhaps we could have figured it out earlier.